have seen pretty much all that material. So, but that said, are there any questions on the material last week? Anything? All right, well, that's good. So if you think of anything in the future, by all means, holler out. So what I want to do then is, let me go ahead and pull up my PowerPoints. There we go. Okay, so chapter 2. So you did the beginning of chapter 2, and the last part of chapter 2 has to do with 3D. And so before we talk about that, just a quick summary. So you, as I mentioned, you did the adding vectors, which is stuff you guys have already done. I haven't had too many questions on that, so because you've probably seen it ad nauseum in other classes. Then you went on to the 2D equilibrium, so physics 44 stuff, and you saw how you're gonna sum the forces in the X, sum the forces.
Okay, sounds good.
All right. So we have 2 equations, 2 unknowns, and then one of the questions I did want to bring up is that the last couple homework problems, and this is something you've probably seen before, but with this, the problem where you're having to calculate, you have this pulley, the picture I have here, that's problem number 9. And just remember that you can cut this cable anywhere you want. So even though P goes straight down at D, you can cut it over here at the location between C and A. So really what you end up doing is you draw C as your point, and then you have one line going off at 25 degrees, and then both of these cables going off at 55 degrees. And then you can sum the forces in the X and sum the forces in the Y. The fact that it goes around a pulley doesn't matter, because remember that the tension is the same everywhere in the pulley. We're not dealing with friction yet, so it doesn't matter. Okay. So that's that for what you've covered. Not too bad. Don't worry, it'll get more entertaining as we move on. Okay, so now the lecture for today, Monday's lecture that's posted in this week, you'll deal with 3D vectors and 3D equilibrium. And the idea with 3D vectors is of course, you can have components, IJK components, and you can have your respective angles relative to the axes. But in this, the idea of a projection is that you can actually, by knowing the force and 2 angles, you can actually calculate all 3 of them. Now, I go over that in detail in the lectures, but just because I want to do an example on that, and I don't want, if it's a new, it probably is, you may not have seen it, I don't want to be completely foreign. So I just want to give you a little bit of the background on that. So let me do this. Doc cam going. There we go. So I'll do that. Go back to my document camera. Sorry, just trying to make sure that Canvas records it, or that Zoom records it. Okay, so you guys are seeing my doc cam, correct? All soon? Yeah. All right. So what we have is, when we're talking about a 3D projection, is if you think about let's say you have a force that's in that direction going up like that. We'll call that F. And so now when we draw it in 2D, it looks like the force is actually in the YZ plane. So we have so it looks like it's in the YZ plane, but it's actually not. It's more like this. So it's sticking up kind of like that. So usually what will happen is you'll be given a force like that, and you'll be given this angle called theta. And so what you can do is you can take this and you can project it onto this plane. So if you imagine this from above, it's going to give a shadow, and you can almost see the shadow depending on where the force is. So if this force is going out, what we do is we draw this, we call this projection, and we call that FH. And then we have this angle relative to here that's called phi. And so by having these two angles and the force, we can then convert this to its I, J, K components. And so effectively what we do is F in this context, if we want the component FZ, then that's just simply equal to F cosine theta. And that's just this side of the triangle. Now, if we want FH, FH is going to be equal to F times sine of theta. And that's this side of the triangle. So it's kind of like if you were to draw the line up here, that would be your opposite. It's the same as this down here. And so think of this as like a slice. It's like a plane. And so now that we have FH, we have this projection onto the XY plane. Now we can relate this force to X and Y. So if we want to know what Fx is, we know that that's just going to be, if we think about it, if this is our hypotenuse, and we draw a line like that, and that's our 90-degree angle, then Fx is going to be equal to Fh sine of phi. But we know Fh is F sine theta, so we can write Fx as F sine theta sine phi. And then we can do the same thing with y. So Fy ends up being Fh cosine theta, I'm sorry, cosine phi, and or Fy is equal to F sine theta cosine phi. And that's pretty much it. And so the reason, I mean, this in and of itself isn't that spectacular, but what we'll do is we'll use this then to manipulate and find, because a lot of times in subsequent chapters, we want to know what the force components are in IJK so that we can actually do something with them. And if all we have is this force in these two angles, then it allows us to find Fx, Fy, and Fc. So now we know that F, we know is just Fx I plus Fyj plus Fzk. All right. So you'll go over that in the lecture that I posted, and this is just kind of a little summary. And then I'll go in there in the lecture. There's more equations that you'll probably want to jot down, just because they may come back on a quiz or on an exam. And my quizzes and exams are open notes, so but it's the time limit's usually not enough that you're going to learn the material during the quiz or the exam. So it's probably better to, as I recommend, is have notes that are relevant to the different chapters, and just have it on one consolidated sheet. It'll probably make it a lot easier for you. Okay, so with that, go back to PowerPoint. And so what this is this is an example of what would you do with these forces now. And so what I want to show you is So you guys should be able to toggle between the .cam and PowerPoint. So the PowerPoint has the actual problem. So I'm not going to do the entire problem, but I'll show you the first one. And if you wanted to, you could do the whole thing. But effectively, you have these three forces. You have a tension in AB, and you have it in AC, and you have it in AD. And I add the 900 pounds in AD. And so the question is, what are the total resultants of all of those? So if you were to add all three together, what would you have as a resultant? But let's just be, you know how to do resultant vectors, so that's not an issue. So let's just look at one of them. And if you understand that, you could do the other three just for the sake of time. So if you look at what I have on the .cam, I've drawn out the dimensions. And so one of the things that you'll notice right away is you have this force that's coming down. And so this force has a projection onto this line here, just like the other force did. It doesn't matter if it's going down or up. So you can consider that this line here is the projection of this force onto the XY plane. And so in order to solve, it can be helpful to know, what are the particular dimensions. So for example, if we look at, for one, this is our angle here that's going to end up being phi, because that's going to allow us to find our X and Y value. So if we do that, what we end up with is, we know it's 12 and 18, use Pythagorean theorem, we get 21.63, and then we can calculate that angle with tangent, and it turns out that angle is 33.7 degrees. So now that we know that angle, then we'll hold that for now, and then we can also figure out what is this angle up here, theta. And so theta, of course, is just going to be the inverse tangent of, we know the height, we know it's 36 feet tall, and we know that distance there is 21.63, so now we know that angle is 31 degrees. And so, and then these are for the respective other ones, but let's focus on these for now. So now that we know those angles, what we can do is calculate what's what. So we know that tension, whether it's tension or force, same thing. So we know that tension AB, the vector, is equal to the scalar AB times the unit vector AB. So that's really what we're trying to find, is this. We want to know what that vector is. And so we know that the tension AB Z component in this case is just going to be this side of the triangle, just like before. So it's going to be equal to 700, because that's how much 700 pounds is the scalar value, and then times the cosine of theta. So 700 cosine 31. And because it's going down, you have to add a negative sign in front. Okay? And so that ends up being, that equals 600 pounds. So if we were to have our tension AB vector, we know it's going to be equal to something I, something J, and then minus 700 K. All right, so there's our K component. And then just like before, we just come down here to the base, and we know that our projection is just simply TAB, then I'll just call it H for horizontal. And you can come up with your own convention, doesn't matter, as long as you keep track of it. But that's going to be 700 sine 31. And that ends up being, and this is phi, of course, and that ends up being 360 pounds. Oops. So I should have written sine of phi, sorry, instead of just jumping to the number. That's a bad habit. It's good to put the variable first and then that. So that was phi. So we got TABH 361, and then do the same thing with to get x and y. We know that TABX is just going to be what? It's going to be TAB horizontal, and then that's going to be times the cosine of phi, and TABY is going to be TABH times the sine of phi. Okay. So now you could use the ratios of the sides. You don't have to use the angle. And that's, so for example, in TABX, if we were to expand this out, really what is that? It's the same as saying TABX is equal to what? 361, because that's our H. And then you could just multiply that either by cosine of 33.7, or you could say 361 times the ratio 18 over 21.63, which is your triangle, because cosine of 33.7 is that. So either one works. As we get later into later chapters, we'll probably use ratios more often just because they're quicker. But again, if you prefer angles, you can always convert to an angle and then convert back to a ratio. So when we do this, we end up with this value is equal to 300 pounds. And then if we plug in the same thing down here, we get 361. And then for that, we have sine of 33.7. And this gives us negative 200. And we're getting the negative 200 is because if you look at here, we're going this way in the negative y direction. So our final answer is 300I minus 200J minus 700K, and then, okay?
I
Now,
think your camera might be out of focus.
I went through that kind of quick. Does any questions on that? Does that make sense? I know you
I
guys.
think your camera's blurry.
Professor,
Is it blurry?
Your camera is out of focus.
Is it out of focus? I'm sorry. Has it been out of focus this whole time?
Oh, I think last
No,
name
not
should
the
that
whole
help.
time.
Is that better?
No.
All right, let me turn off the light, see if that makes a difference. It's got very limited. Is it still good or bad? Indifferent?
It's good.
That's better.
Yes, clear now.
Is that better or worse?
Yeah.
Yeah, it's clear.
That's better.
Is that clear? All right, thanks for telling me. Yeah, because I have no way of telling because it's just this little image, but yeah. So sorry about that, but I might get a little shadow effect there. So does that make sense so far? Any questions on that? I know I went through that kind of quick, but I just wanted to, mainly I wanted to go through it because when you guys look at the lectures this week, it won't be something completely new, at least you'll have seen it. That's why I try to do that in these live lectures on Monday, is kind of give you an idea what you'll be looking at the following week. So anyway, so that's what you would do. You can do the same thing for each of the other ones. You can see it's the same method. You find the little angle up here, in which case I called it gamma. Over here, it's called alpha. These two angles are actually the same because both of them go out 12 in that direction. So, but once you do a couple of these, they're fairly easy. And again, they're just means to what we'll be doing in chapter 3 when we'll actually need the total forces in order to find moments about points and lines, which we'll touch on today. All right. Good. So if we look at our next slide, one of the, and this is the next topic, is the idea of equilibrium. And this is the last thing that we'll talk about in chapter 3. I'm sorry, chapter 2. And so in equilibrium, what we have is so in this problem here, what you have is you're asked, oh, sorry, I can show you next thing. There we go. You want to know the maximum weight of the crate so that the rope does not exceed, the tension in the rope doesn't exceed 450 pounds. So what you have are these components. You have basically A, B, C. Those are the locations of each one. And what we want to figure out is what are the locations? What are the respective tensions in each one? We know it can't be more than 450, so let me back up. We want to know the maximum weight of the crate so that it's not exceed 450, but first we have to figure out what the relative tensions AD, AC, and AB are to each other. And that way we can know what we're doing. Okay, so how do we do this? First off, and this is a 3D equilibrium. I'm going to sketch it out, but I'm not going to solve it just for the sake of time. But you know that sum of the forces is going to be equal to 0, obviously. And so we have the force or the tension, whatever, either one's the same. The force BA plus the force CA plus the force DA plus the weight equals 0. So we know that we have that, and that's pretty much standard for any statics problem. So what we then need to subsequently do is we need to make each of these determine what each of these vectors are. So we know we have FBA, we'll start with that. That equals the scalar amount of BA times lambda BA. Okay, and then, so let's just look at that example first. So we know that RBA, the distance between RBA, is just equal to RB minus RA. Right, actually those are points, so it's my vector. And so we know that if we do that, we know that RBA is just equal to minus I plus J plus 2K. All right. So this problem, all this problem represents is now that we have three dimensions, we just want to use the idea of these tension vectors to solve something where we have multiple unknowns. So this is probably something we've seen in other classes, but anyway, going back to this. So what I've done is I've found essentially RBA minus 2 plus J plus 2K. So that's just the distance from B to A. So nothing that complicated. So we know then that our unit vector, lambda BA, and I'm going through this in piece by piece, but in the future, you'll probably just jump right to lambda BA because you'll become familiar with everything. So we know that lambda BA, the unit vector, is just minus 2I plus J plus 2K, and then it's divided by 2 squared plus 1 squared plus 2 squared, and then square root. And that's how you get our unit vector all the time. So subsequently, we know that lambda BA is equal to minus 2/3 I plus 1/3 J plus 2/3 K. All right. So now we have our unit vector, and whether you convert it to decimals or leave it in fractions, it's up to you, whatever's easier. So now I can, if I did the same thing over here, I'm not going to do I'm not going to go through each step, but I would get lambda CA equal to, in this case, lambda CA would be equal to negative 2/3 I minus 2/3 J plus 1/3 K. And lambda dA is just equal to I. So we have those. So then, and so the next step then is to just insert these equations into this. And so what we end up with is if we take our unit vector and we put it back into here, then we know that F, our vector FBA is just equal to what? It's equal to negative 2/3 FBA scalar plus 1/3 FBA Fij plus 2/3 FBA K. And then we have FCA equals negative 2/3 FBA plus 1/3 CA. So plus 1/3. I promise it'll get more exciting than this. And then lastly, just FBA equaling to scalar FBA I. Okay, so this part here, I think you can see it's just a matter of converting these distances. And then, so now you have these three equations. So when you solve these, and this technique we'll use again when we get to chapter 4. But effectively, all you're doing is, in order to solve these, is you know that all the forces in the I have to be the same, J and K all have to be the same. So what you can do then is you say, in terms of I, you just say minus 2/3 FBA minus 2/3 FCA plus FDA. And you know that all equals 0. And you do the same thing for J. You put all the J terms together. So that's 1/3 FBA minus 2/3 FCA equals 0. So if we look at that, then that tells me that FBA equals 2 times FCA. So that's what I've deduced from that J equation. And then lastly, I have the K equation, which is 2/3 FBA plus 1/3 FCA minus W equals 0. So effectively what I have is I have 1 equation, 2 equation, 3 equation. And so what I do, and with this, is I use just some substitution, and that's how I'm able to calculate what I have. So for example, I know up here that if I have FBA equals 2 FCA, then I can substitute that up into this equation, and through substitution, and you can, and for sake of time, you can check this, but what I end up with is I end up with FDA equals 2 FCA. And so therefore FBA equals 2 times FCA. So basically those two are the same. So because I know that, then I end up in the final equation, when I substitute everything in, I end up with FBA, and this is in the last equation here, equals FDA, which equals FCA. And so that's the, or I'm sorry, this is 2 times that. So through substitution, I end up with this relationship. FBA is the same as FDA, which is equal to 2 times FCA. And if you did the substitution, you would see that. And again, I apologize. I want to get through some other stuff before we end. So we come to the crux of the problem, because we know that we can't have any more than 450. That's the maximum. So we say, well, if this was FBA could be 450 and FDA could be 450, but FCA could only be 225, right? It's 2 times that. So if we go back to this last equation, this one here, then what are we saying? And we're saying that 2/3 of 450 plus 1/3 of 225 minus W equals 0. And so if we solve that, we get W equals 375 pounds. All right. Now I know, again, I went through that real quick, but the concept really is, if you break it down, it's just really about breaking these into their individual unit vectors, combining the vectors into their I, J, K collectively, and then just looking at these relationships and then substitution. And that's it. I mean, I'm not meaning to trivialize it. It's just that after you do a few of them, there's no trick to it. It's actually pretty straightforward compared to the math you guys deal with in other classes. This is the math in this class is trivial. Okay. All right. So that's, those 2 examples show us what we'll be covering in chapters, the end of chapter 2. So something like those 2 you'll probably see on the quiz on Wednesday. So I would, something like either a 3D projection or like this 3D equilibrium. And there's examples. So be sure that you look at the last lecture is actually for today. Wednesday's lecture deals with chapter 3. So there won't be anything obviously on chapter 3 on the test, only on the quiz. Okay. So let's talk about moments. This is the beginning of chapter 3, and we'll just touch on this. The beginning of chapter 3 isn't too tough. I find it actually stuff you've seen before. A lot of this should be review. But if it's not, I'm not, just say, hey, I don't understand that. So your silence means that you're absolutely stunned and understand everything I'm saying. Okay. So this next problem, so moments and equivalent forces. So I know you guys have seen, the idea that if you have a object, so there's your object, and so if this is point O, and that's your force, and that's your distance, we know that if we take a moment about O, it's just equal to force times distance. And the distance being the perpendicular distance relative to the force. All right, so nothing new with that. So in 2D, the assumption is that we're always, even though this is a vector, the assumption is that in 2D, we're always going about the axis that is out of the page. So our final answer for whatever this is always going to be something in Newton meters, and it'd be in the K direction, or foot-pounds in the K direction. And we know the convention is if it goes counterclockwise, it's positive, and if it goes clockwise, it's considered negative. So your answer in this case would be positive. It's going that way. So if we look at, so in 2D, it's pretty easy. We just do force times distance, we're done. Now, when we get to 3D, it gets a little more complicated because in 3D, it's harder to visualize and it's harder to draw. So generally what we'll do in 3 dimensions is we have, like a if you have, say, force like this in space, F, and we say we want to know the moment about this point O here, then we'll just draw a line to here. That's our R vector. It's our force vector. And we'll say it intersects at point A. So if we want to know that the moment created by that force about point O, moment O, then it's just equal to R cross F. That's it. And the thing is that R can be any point. Oh, obviously the point's defined, but it can be to any point on the force. It doesn't matter. So I could have drawn R to go to here. I could have drawn R to go to here. It doesn't matter. So the convention that we use in this chapter is we say R is A relative to O, meaning we go from O to A. So you always draw your R vector going from the point to the force, never the opposite. And then we cross it with F, we set up our cross product, and we're done. And that's it. So, and our final answer then, when we get our answer, it's usually a vector. It is a vector, and it usually has multiple components, I, J, K. So that's a lot easier than trying to figure out what the perpendicular distance is to that. But for 2D, it works fine. So if we look at the example that I have on the screen, then you can see that for something like that, if you have, a half circle, it's kind of doing that thing. And so here's your force of 500 newtons, right? And here's your point O, your origin, or that's the point they want you to take the moment about. And again, I go over the theory and the details in the lecture, so this is just kind of a brief overview to plant some ideas in your head. So we know that if we want to find the moment about O, then the vector we know goes on forever. So we could trace the vector all the way back to here, and then we break it into two components like this and like this. And then we know that this, since it goes right through O, won't count. And so if we say a moment about O, it's just going to be equal to, well, we know it's 500 newtons. We know that's 45 degrees. So this is our perpendicular force relative to that. So it's going to be 500 newtons cosine. Actually, I'm sorry, sine 45. I don't know 45, but sine 45 degrees because we want this part of the force. And then that's just going to be multiplied by 3 meters. And then that gives us our answer. So it's just 1,500 times square root of 2 over 2, or essentially 750 root 2. So that's our answer to that. Now, you could have done it out here, and it's a little, if you'd done it out there, it would have been exactly the same. If you'd done it out here, then you would have still had these forces broken into two pieces. And this piece here would have been, going that way. But this piece here actually would be going the opposite way. So you have to subtract that off. And so you could write it out, but for sake of time, I'm not going to. But, this would essentially be the 500 newtons sine 45, and then it would be 3 meters plus this distance you have to find, which would just be 3 cosine 45. And then this here would just be, this height here for this would just be the 3 sine 45. Anyway, point is that as you go through these problems, you'll see that the make it as easy as possible for yourself. If you can trace the force back to a point where one of the forces is eliminated, then by all means do it. But if you wanted to do it up here, it would work just as well. Let's see. Actually, let me show you that real quick. So if we did do it up here, we'd end up with 500. So moment about B, moment about O, would be equal to 500. So now we're looking at this piece here. 500 sine 45. So that would be this component. And then that would be times 3 plus 3 cosine 45. And I got that from this 3 plus this 3, because that's 3 cosine 45 gives me that extra distance. And then that would be good for this piece. And then this piece would be minus 500 cosine 45. And then its distance is just 3 sine 45. So you can kind of see that this here is the same as this up here. And this times that is going to basically eliminate that. So that's where we come full circle. And so there's really no advantage to putting it up here because it's going to come out exactly the same. Now, the second thing that you're going to see in this chapter, and so, oh wait, before I actually we have 7 minutes left. So let me just mention real quick. So if you wanted to, if you want to find a moment about a point, like I just showed you that in 2D, if you want to find a moment about a point in 3D, like this one here I just showed on the PowerPoint, then on a problem like that, what you're doing is you have your moment about A, and that's going to be equal to R cross F. So that's your governing equation. All right, so what we have is we have this object, and then we have this comes out and back again. And so there's a force going down like that. So if you, when you're doing this, you want to convert that to a force vector, and you want to get the R vector that goes from here to here. Now it could go from here to here, or it could go from where it intersects down there. It doesn't matter. But I think this is easier. So if we find this R vector, this is point A, and this is point C. So RC relative to A is just equal to 0I plus 90J plus 100K. And all I did was go from A to C. I just made that vector there. And then with my force vector, all I did was I wanted to, in the force vector is actually at P, but it doesn't matter, it equals 200 newtons. And so I know that F equals 200 newtons times that, whatever that unit vector is. And so if I look at the unit vector for this distance, I can see that lambda is just going to equal negative 70 in the I plus 0J minus 100K. And then if I square root it, I get 122. So then if I go ahead and multiply through, sorry, it's getting kind of messy, but my F vector ends up being 200 times 70 over 122 I, and then minus 200 times negative 100 over 122 K. So that's my force vector. So then this just simply equals negative 114.7 I plus 0 J minus 163.8 K. Sorry, I'm going kind of quick. So let's slow down here. This will be the last thing we'll talk about. But so you have MA equals R cross F. So we found our RC relative to A, and we found our force. So once we do that, it's just R cross F and we're done. So we have this and we have this, cross product those, and you get your answer. If you want to go ahead and try that, then the answer is negative 14 point, oh wait. Yeah, it's negative 14.74 I minus 11.47 J plus 1032 K. And that's in, that would be in Newton meters, 10 point. All right, so that's the answer if you want to try to do that. And I know we're almost out of time, but I just want to say one more thing. You will also be doing this week is, before we talk next week, is the moment about a line. So the difference with moment about a point, moment about a line is you use this equation down here. So if you're doing a line, then M is equal to the unit vector of the line. And so let me just schematically, what it would look like is you have, if I have this force out here, and there's my, so that's my force, that's my R vector, and that's my point. Let's say I have a line, you know. So this would be my line. And so if I want to know what the moment about this line is here, then it's going to be, let's say it's line AB, it's going to be the unit vector line AB dot product with R cross F. So it's just one extra step. This R cross F is exactly the same as here. It's the distance from the line to the force, and it's any point in the line to any point in the force can be your R vector. The force, again, is just a vector. And then this lambda AB is just the unit vector of the line. And the difference here is your answer is a scalar. So when you do this, this ends up being a scalar. So you get something like 110 Newton meters. And that's it. It's not a vector. And you would see that, and I point this out because it's a common mistake is to make this a vector. It's not. Anyway, I know I went quick through a lot of that. I apologize. I'm trying to just condense what you're going to see this week. So I know I planted the seeds. If this was your only lecture, I think it'd be very difficult to understand. That's why hopefully with this information plus the lectures you watch, that'll ring a bell. Okay. All right, we're out of time. So I will see you guys in office hour or next Monday. Don't forget our quiz is on Wednesday morning. So you'll be taking that during this time instead of being a lecture from 8 to 9. I will send more information out on Canvas, okay? All right, thank you guys. Have a good day.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.